And I apologize in advance. It's going to be a little more technical than the wonderful talks we heard this morning, such as the spirit of the subject. Enumerative geometry is about big numbers and complicated formulas, and I would be doing injustice to the subject if I don't have any formulas in the talk, but I'll try to. And in terms of acknowledgements, I want to say the general picture that I want to explain is very much a product of thinking of a lot of people whom I listed here, and more. And what's the subject is what's in the broad stroke, what's the outline of today's talk is I want to talk about one instance of a phenomenon which happens in a lot of in biology. So in trying to present formulas in less formulaic way, I've chose to use a bunch of biological metaphors. So this, I don't know if you're going to like it or not. But what often happens is very distant branches of the tree of life, long separated at the beginning, then come close later. Like, well, I don't know, like human and parrots, they have something to talk about. But if we go many generations back, that wouldn't be the case. And so today we'll be talking about the geometric representation theory in enumerative geometry. The genesis of these two things is quite distinct. And I will talk about the genesis of the problem on the geometric side. And so this would be a brief account of the evolution of some particular set of problems. And maybe the place to start is did I press some? No. The place to start is to talk about the subjects we all know and love. Namely, we will talk about just moduli of curves. And if you want a smooth genus G curve, it's at marked points. If you want to make a compact moduli space, following the linear Mumford, you allow certain singularities. So there's a compact moduli space for such objects called the linear Mumford moduli space on stable pointed curves. And over this algebraic variety, there are natural vector bundles. Well, for example, the one which is of particular importance to many people here is the Hodge bundle. And the fiber over genus G curve is the space of holomorphic it's the G-dimensional space of holomorphic differentials. It's also the dual of the first cohomology of the structure sheaf. And maybe simpler classes are if you have a pointed curves, then at every marked point you have the tangent line to the curve itself. And also the cotangent line. It's just easier to think about the cotangent line. And so I have a line bundle and corresponding divisors. And this of course, very closely related to Miller, Morita, Mumford classes, people, again, very familiar here. But the particular theorem I'm going to mention in the next slide, this has to do with intersection theory of these line bundles. And this is a famous development in physics and mathematics. This is Witten's KdV/Virasoro way of computing all these intersections. And that's, again, the carbon dating gives this an age of about 25 years ago. And many people in this room contributed to this being a mathematical theorem. Dmitry tied up some not so tight end in Kontsevich's paper. Mariam gave a wonderful proof, as did Maxim, who's still, I was told he's still at the mercy of British consulate. So hopefully he comes here. So and so that tells you, so you have some moduli space, you have divisors on it. You can construct them, you get some numbers. And if you want, since you also had a rank G bundle, the Hodge bundle, the bundle of holomorphic differentials. And of course, you want to throw in the Chern classes of that. You can do it formally by Riemann-Roch type computation. It's for what I'm going to explain later. Riemann-Roch it's never a good idea to seldom good idea to use Riemann-Roch in this situation. And to have a very simple example in mind, you can think of Weil's dimension formula. Weil's dimension formula tells you that the dimension of reducible representation of a Lie group is some very nice product. This is also the Euler characteristic of a line bundle and flag manifold. And you can, to prove Weil's dimension formula, they're very short proofs. We teach undergraduates. to do it by Riemann-Roch, that's a serious exercise. So now the point I was going to make. So this is in the past. This is a long past, and the what's in the present is or maybe not in medium length past is even if you only care about moduli of just Riemann surfaces, just algebraic curves, it may be a very good idea to study them together with extra data. And the kind of extra data we will allow is a map to some algebraic variety. For example, you can take a curve together with the embedding of projective space. That will be an example. And so if you just the Lie-Mumford space is a wonderful algebraic variety. This is not the case for the moduli. This from natural moduli spaces, but they're not by themselves. They're not particularly nice algebraic varieties, and in particular, they jump wildly as we deform X. Right? I mean, this is looking for curves is like looking for rational points, and so it's just kind of this has this sort of flavor, and one deals with it by bringing in deformation theory and giving the spaces, well, the actual spaces jump as we vary X. Like, say, for example, we look for curves in hypersurface. We vary the coefficient, the actual spaces jump, but we bring deformation theory to define a family of cycles that glues into one cycle over the family. So if those of you more analytically minded can take the following definition, that having a holomorphic map to a given X is like solving a particular D-bar problem, which is not in general position, but you can replace it by the space of solution to a suitably generally perturbed D-bar problem. And that would be the space of solution, that would be the virtual fundamental cycle. And so that virtual dimension here is given by, again, well, this is an easy computation, and it comes down to this formula. And the reason I wrote this formula is that from this formula you see that the dimension X being a threefold is a very, very special case because the genus term drops out. So you see, it's maybe a slightly contrary to intuition. The expected dimension, if you think of Riemann-Roch formula, it has, if you have if you have a vector bundle on a curve, it has degree plus rank times 1 minus g. So the higher the rank, the smaller, in fact, is the Euler characteristic. So the higher the rank, the less is expected dimension. And so exactly for threefolds, the 3g minus 3 in the dimension of the moduli space of curves, and this rank in Riemann-Roch for a curve, they exactly balance out and you get no genus dependence. So this is a very special case and will be important for what happens later. So like I said, you get this moduli spaces get a particular homology class of this expected dimension, and one defines the Gromb-Witten invariant or the Gromb-Witten counts in X as the integrals against that virtual fundamental class of natural cohomology classes. And the natural cohomology of the class is the same old suspects. The ones we had these Witten type divisors, we had the Hodge, Chern classes of the Hodge bundle. And also we have, since we have a map to X, we can pull back by evaluation any cohomology class from X itself. So that gets you more classes. And so this enjoy very nice structural properties, and in particular deformation invariance. This is why they sometimes call Gromb-Witten invariants. Right? And so my next goal is to explain how the problems about just MGN, no without X, how they sit inside this big, so in the world of this all possible threefolds, how the old things sit, one way in which just the question about modular curves, how do they sit inside this bigger theory? And the first point to make is that even if there is no, even intrinsic to your problem, there is no group action. it's still very beneficial to think about equivariant counts. And the one thing that allows you to do is it allows you to replace study things like curves in X cross a line. And that's of course because it gets awfully non-compact space, because once you move to any curve, any connected curve is going to map to a point on that line, and that point can be anywhere. But if you study it with respect to GL1 acting by rotating of that line, then it's not that bad, because if you study intersection theory equivariantly, you only care about the fixed locus and the normal bundle to it. And the fixed locus, obviously, if you have, so this is, you have to look at this picture here. So this is my X cross line, and I have a GL1 rotates this around, and so the only thing that the only way such map can be fixed is that the curve really maps to the fiber over 0, really maps to the X itself. There's no other way. And the normal bundle, whatever it is, it will have the normal bundle to the curve, which tells you how can I deform my curve that had some direction along X and a trivial direction along that C. And so now this will be also my chance to explain you how the virtual class computation, what's the spirit of the virtual class computation. And that is that, so if you have, in other words, this, again, so this is, you have a curve sitting in X, and it now gets the trivial normal direction. But this trivial normal direction has a weight. It's a representation of my GL1, has a weight, which will denote T. And so there's a deformation direction, which it says the curve rigidly moves along my C, and so that gives me, well, somehow properly speaking, the deformation space is just the sections of the trivial section of the trivial line bundle. So it's just one-dimensional space, but that one-dimensional space has my group action. So its Euler class comes out to be that T in denominator. The deformations go in denominators, and the abstractions, which in this case will be the first cohomology, or the dual of the Hodge bundle, they go in the numerator. And so then, that's the Euler class, so again, the abstraction bundle is the first cohomology of the normal bundle to the curve. So that will be the dual of the Hodge bundle, because H1 of OC is the dual of the Hodge bundle. And then if you take the Euler class of a vector bundle twisted by a one-dimensional representation, well, that come out to be just the Hodge polynomial of my original bundle. And so this says this example says that if in equivariant theory I take my target X and I cross it just with a line, then all I get is an insertion of the Chern polynomial of the Hodge bundle. So that's a yeah.
These are terms in what?
So when you do equivariant integration, that means you integrate over a fixed locus, and there's some normal bundle contribution. The fixed locus are just old maps to X, and the normal bundle contribution in your previous integral, you just get the Chern polynomial of the Hodge bundle. More questions? Okay, well, let's move on. And then if you want to manufacture Witten's classes, we can study the following type of problem. If I have in my threefold, if I have a divisor, I can insist on my curve intersecting this divisor with some fixed multiplicities. Meaning, if I pull back the equation of that divisor, it's given by one equation, that's a collection, this will be a collection of points on a curve with some fixed multiplicities. And those multiplicities, of course, have to add to the topological intersection of your curve with the divisor. And so this is a legitimate question to study. And in particular, I can ask this question in the situation when my threefold, so this is kind of loaded slide, so maybe you look first here. So the threefold is just C2 cross P1. It's the simplest possible threefold. And my divisor is the fiber, is the C2 with fibers over infinity. And then now, in this geometry, I have an action of a three-dimensional torus, if you want, which scales two of the directions of the torus scale the two axes of C2, and then there's one scaling P1, leaves my divisor fixed. And so if I look at the fixed locus, well, here's the computer error. There should be like a bubble here. But the actual fixed locus of this action is very simple. Your curve has to go to the origin, and then it has to have these bubbles that each one of these curves is just a copy of P1, and each one of them maps to P1 by the map that Z goes to Z to the power mu I, where mu I are the multiplicities with which it's supposed to intersect the infinity. So the actual fixed locus is nothing but the old MGN bar. But if I now bring in the abstraction theory, I get 3 copies of the Hodge polynomial of the Chern bundle, because I have over my bubble, I have 3 normal directions to it. On the previous slide, we saw that each normal direction gives you one Chern polynomial. And if you analyze what's the deformation theory at that node, that gives you this gives you the denominator in which the Witten divisors stand. So the way the Witten divisor are packages in this form, which of course what you should do is expand this out. This is some nilpotent element in H2. So you expand this out, you get a polynomial. And so that says that this particular function, which depends on, well, I guess it depends on that, or if I study curves of degree d, then the numbers mu I, the degrees with which these individual bubbles map to P1, they form a partition of D. And so this is my partition which I denote mu. And then there's also genus, so I have a function like that, which have a product of 3 Chern polynomials of the Hodge bundle in the numerator, and such an expression in Witten's classes in the denominator. And it's very clear that if I vary this overall general overall partition, this packs the entire information somehow. The entire information about integrals of MGN bar, which involve arbitrary number of Witten divisors and up to 3 Chern classes of the Hodge bundle. And so we're going to talk about this sort of functions today, and but we're going to talk about them from slightly different angle, and that we have to remember now that I chose here this instead of C2 could have been anything, and this could be C to the n, and then I'll have n plus 1 of these Chern polynomials. What's special about 3 is that in 3 dimensions we have a correspondence between counts in Gromb-Witten theory and something known as Donaldson-Thomas theory. So what is Donaldson-Thomas theory? It's a long story, but for the purposes of this talk, I can try to explain it like this. So in Gromb-Witten theory, you study maps from a curve to your threefold. In Donaldson-Thomas theory, you study not one-dimensional subvarieties of the threefold parametrized. It means you study curve not parametrized, but instead you study them as defined by equations. It's something cut out by equation. When you cut out something by equation, you cut out what you cut out is really a subscheme. Could be some multiplicities and so forth. And there's a parameter space for subschemes or things defined by equations. It's called the Hilbert scheme. And in this case, you take the Hilbert scheme, which cuts out a curve. So this means it's the Hilbert scheme for subscheme whose Hilbert polynomial looks like this. It has nothing in full dimension, nothing in divisorial. It is a curve of some degree d, and then it has the constant term of the Hilbert polynomial, which is the Euler characteristic of the structure sheet. So in general, if you on the fourfold, the Hilbert polynomial will have 4 terms. So the first 2 vanish, and then d and k. And the shape of the correspondence is that here everything happens for a fixed degree, but here you sum overall genus, and you put a variable u to the 2g minus 2. And the point about the fact that in 3 dimensions the virtual dimension is independent of the genus is that you can stick one and the same integrand here for all genera. So this makes sense because it's the spaces of the same dimension for every genus. So this gives you a series in U, and this gives you a series in the variable Z, where Z is now paired to the Euler characteristic. And this is so for a smooth curve, this number chi is 1 minus G. So you'd think the relation between Z and U should be something like Z being 1 over U squared. But it's nothing like that. It's in fact Z is exponential of IU. And it's about expanding the same function at two different points in the complex plane. And why I'm bringing this up is because this story about intersecting curve with the divisor, that has a much cleaner restatement in the world of subschemes. Namely, if I have a one-dimensional subscheme, here my curve C, that intersecting with an x, it just means I impose one more equation, the equation of x. And so I have a map. Well, in fact, it's a rational map, but let's not worry about it now. So from the Hilbert scheme of curves in 3 dimensions, I have a map to the Hilbert scheme of points in 2 dimensions. And then whatever I can package enumerative information about, so the geometry here, so the geometry, you should imagine that maybe, no, first, let me backtrack a sec. So if you have so you have a moduli space of one-dimensional subscheme in 3 dimensions. You intersect with the divisor. You get a map to subscheme of that divisor. You get a map to the Hilbert scheme of points now in the surface. And then if you had say a homology class on it's like a virtual fundamental class on the space that parameterizes my curves C, I can just push it forward and get a homology class, or cohomology class is all smooth spaces, and that class in cohomology of the Hilbert scheme of points on the surface is the way I can package my enumerative information. And what I should, as I push that class further, as I push that class forward, I have to attach. It's like a story, box you send to a storage. You have to attach to it a label, and the label should be the information you lose in this process. Namely, of course, in this process, you lose the information about precisely about this K-theory, precisely about this vector, about the degree and the chi. This you don't know. And so this is you. In other words, if you sum up over all possible degrees and Euler curves in general of my curve C, I get like a series in cohomology classes on the Hilbert scheme of points on the surface, and that series is like a very detailed representation of the three-dimensional enumerative. It's an infinite series in many variables, and it's a very detailed representation of enumerative information from 3 dimensions. So maybe I should somehow point out that in fact this is some kind of series in many variables, because, like I said, the exponents of that series, they keep track of what was the degree and the genus of the curve in 3 dimensions. And the way to think about these variables is really, you should think of that lattice as the Picard of the Hilbert scheme, so of D. So have I lost everybody, or is somebody following? Maybe there's a question. Because this is so right now I've defined for you, maybe you can, there was a bunch of transparency just to connect this problem to things people may or may not care about MJN bar. Like this series in particular, if I take my threefold to be P1 cross C2, and then divisor to be just one of the C2s, that series will package the entire information about the Witten classes and
So what is the overall goal? You're describing Witten, you're describing Carlson Thomas. What's the overall plan?
Okay, that's a good question. I'll get to that maybe if there's no further questions. Because this kind of leads me to the next transparency, yeah.
Maybe I have a question.
Sure.
So this map from the Hilbert scheme of curves
Yeah.
X intersecting D to
Right.
points on D, does that have to be done with virtual things, or is it literally? I mean,
No, it's
not
so.
obvious to me that these points move in a flat family as the.
No, so the way we apply it, we apply it to some. So you can. No, that's a good map as long as a whole component of C doesn't fall into D. So you can discuss what happens there. But in this type of equivalent computation that I discussed, 2 slides back, that you actually integrate over an open locus, which is good locus for this map. So but you can also deal with that with this kind of that situation too. Okay. So now I can, if no questions, I can go to that. So the statement is that this sort of data, like again, the data is it's a vector. So if you have a surface, you imagine C2. In the case I was trying to promote, the surface can be as simple as C2. You have a series, the variables in which go over effective classes maybe go over some. The exponents in the series of which go over some cone in the Picard of the Hilbert scheme. Well, the Picard of the Hilbert scheme of a surface is the Picard of a surface plus 1 more z. So meaning for C2, this will be just integers. So for C2, you get a series with in one variable, some term with no z, some term with z, then z squared, and so forth. That packages each term is an element of cohomology of that variety, and that series packages, in some effective way. If you're smart about it, this sort of thing packages the entire enumerative information we have about threefolds. I was going to get to that point slightly later. The goal is to understand this series. Okay. And then move on. Now we. All right. So this series now this I'm going to say that for there's an answer. We know what that is, and I'm going to explain an answer. I'm going to state a fundamental fact, and in the fundamental fact, it's fundamental because it involves a fundamental class, and it involves the fundamental solution. So if you combine the two, this fact ought to be fundamental. And it says that object, which is some series in cohomology, is in fact action of some operator on the fundamental class, and the operator is nothing but, in this case, inverted, a fundamental solution to certain. In one variable will be ordinary differential equation. In many variables, it's a system of such. So it's a fundamental matrix of sections of a certain connection. And so the point of that, the transition, elementary point is that the transition from the coefficient differential equations to the fundamental solution is it's a purely mechanical transition, but a transition that somehow, if you have right, if you know the coefficient, then you can certainly write. If you know the coefficient of your equation, you can certainly write out the coefficients of the solutions. It's a kind of mechanical procedure. But of course, the point is that the equation here has a much more compact form, and that thing achieves a certain really dense. So I'm gonna instead of formulas that otherwise would take. If you've ever seen any formulas for Hodge integrals, this will take a long time to state. But the actual differential equation, that would be some very compact form to store that information. And this differential equation is known quantum connection. It's slightly unfortunate because, well, anything of physical origin gets an adjective quantum more or less automatically, and so it's really somehow to call, and somehow analysts ask you what you do, you say, well, it's a quantum connection, and it turns out it's a linear differential equation with regular singularities. Then you think, somehow the world is coming to an end. So it's analytically, it's a very simple thing. It just has this name. So and it's been computed. So in fact, this is a kind of a central point in proving this Gromov-Witten-Donaldson-Thomas correspondences, among other things, is that equation, which I'm going to get to that, the equation. So I guess after the slide, so before the slide, the goal was to compute the function v. After the slide, the goal is to compute the differential equation. And so that equation, that's kind of essential point in proving like Donaldson-Thomas equals Gromov-Witten, has been computed for the Hilbert schemes of ADE surfaces, and that's enough to get all threefolds. But in fact, in general, the Hilbert scheme of ADE surfaces are examples of something known as Nakajima varieties, and the problem can be studied in that generality. And in that generality, it actually has a kind of uniform answer, which is I'm not going to explain what Nakajima variety is, but it's something which is just as good as the Hilbert scheme of points on ADE. So ADE surface is a resolution of a surface singularity of ADE type. The A0 surface is C2. This is somehow the most important surface. So that general formula that Davesh, Molek, and I proved is going to be stated on the next transparency if I can find the right button. Oh, sorry, yeah. So this first we're going to get. So this pause for a biological metaphor, and this is it. Is the differential equation is like a silkworm that in purely, well, I cannot say exactly mechanical way, but sort of straightforward manner produces for you the silk, and then you get the thread. So you just solve the differential equation, so you get that vertex function, and then from that vertex function, it takes a certain mastery to produce the complete variety of the silk clothes we have, but that mastery has been achieved in the work, but most importantly, in the work of Pandey, and Pixon, for which we've rewarded them with the Clay Fellowship and Clay Prize, respectively. So the whole variety of threefolds is, in fact, you don't need three colors. You don't need all these threads. You only need three colors, to produce. I mean, quite literally. Because the cobordism in this dimension, dimension 3, so you only need three things to three. That's clear. So that's going to be about. So the rest will talk about this. So and so that general formula for the quantum connection, the formula, yeah. Sure. This one. It's a theorem, yeah. It's not a complicated theorem, that's why I call it fact.
So it's a simple theorem, but the really hard thing is to figure out which linear differential equation.
Exactly, yeah. I mean, any function whatsoever is a solution of differential equations. This is somehow, it's not saying much. But it's a, yeah, but it's a point here is the differential equation is something super nice here, yeah.
So the fundamental fact is that the differential equation is super nice?
Yeah, exactly, yeah. So how to say it? The logic here is like this. You geometrically define a certain equation, and you prove this formula. And then a miracle, I mean, not a miracle, I mean some kind of, I don't know, it's not a miracle, we understand it now. But then something happens, and you're actually able to compute that differential equation. First, you define it geometrically, but it somehow doesn't say much. Because like I said, any function in the world will solve some equation. The point is that this geometrical defined operator can be actually evaluated as something reasonably nice. And you'll be the judge. So the formula is this. So this is the general formula for any Nakajima variety. It says that connection, if I go, so this has to be a connection on peak. So if I go in the direction of lambda is in peak tensor C, well, it's a connection on peak tensor C if you want. So then, let's say peak, go in the direction of some line bundle. then the connection matrix first has a constant term which is independent on this degree variable. Z was to keep track of the degrees. And that further has constant term, which is just the cup product by the divisors. So it has to be an operator cohomology. And there, of course, we have cup product by the first term class of line bundles and operator. And then the rest is something. So first it goes over, first there's a sum over, so it's going to be, in the end, it's going to be some Lie algebra. So it's going to be a sum over positive root of a certain Lie algebra. But those roots, each root in itself is a curve class. So Z to the alpha is the kind of variable we want. So it's like, the exponents here keep track of the curve classes. So Z over alpha 1 of Z minus alpha, that's this term that has regular singularities. And then with each root, you get something like Casimir-looking expression written in terms of a certain Lie algebra that acts by correspondences. We'll review that notion later. There's a way for Lie algebras, that's the whole point. The whole point, no, not the whole point. One of the main points in geometric representation theory is that there is a way for Lie algebras to act not by matrices, but by correspondences between various algebraic varieties. And in particular, they will act on cohomology of those respective algebraic varieties. And so then if you have a weight space, so in Lie algebras, you have in respectable Lie algebra, you have a weight decomposition. You have the space, the weight, the root decomposition. Root alpha would be paired with root negative alpha. And so in particular, in the product of these two root spaces, there's a canonic intensor, this kind of Casimir-looking expression. And that comes with the coefficient, that coefficient. So I don't know. Is that nice? It's nice enough? I think it's okay. So I guess I explained the terms in this, right? So it's a connection on the cohomology of some variety. I didn't tell you how the Lie algebra acts, but it does act. We'll discuss that. And if you have a finite dimensional Lie algebra, such objects are well known in Lie theory. And this in particular, you may want to look at it's a bunch of papers by Valerio Toledano-Laredo on the subject. And so now, and the actual goal of this talk, so this is, so the goal of the talk, 3 transparency ago, the goal of the talk was to compute this function v. Then it became compute this differential equation. Now differential equation has been computed, so we somehow seem to be without a goal. And the actual goal is to promote this to, in fact, a Q difference equation. Just, if there is an aspect in which this talk may, somehow attempt to resemble the wonderful talk by Peter we heard this morning, is that had first differential and then this Q difference thing. So that's the only way in which I can somehow try to be like that. So and the point is that if we now forget everything, not forget everything, upgrade everything, all the questions I've asked, you can be asked in a covariant K-theory. In fact, much more natural. And that in the K-theory situation, you can also prove there is now a Q difference equation, where Q is the variable. Remember, I had that P1, and the actual element of the multiplicative group acting on that P1 is Q. And it's interesting to study this enumerative K-theory. This talk has to be, although it doesn't look this way, but it has to be finally presented, and this is the reason I've chosen not to go into the discussion. If you look at my website, there's a bunch of slides there about why is it interesting to study K-theory. So, and there was a clear sense in what the analog of that differential equation should be in now we go to K-theory. And in fact, so for finite, like I said, for finite dimensional Lie algebras, which is not the case of interest to us right here, but it's been understood, and in particular this expedition in There's exposition in the paper by Balagovich how a certain object called dynamical quantum affine Weyl group. Okay, well, it makes a talk by itself just to pronounce this object. How this is generalization. How this is a generalization of that connection, and when we think how can a Weyl group be a generalization of connection? Point is that this is an affine Weyl group. In particular, it contains a lattice, and an action of a lattice by some operators is like Q-difference equation. So that's that part. There's some operators in the lattice part of the Weyl group that give you the needed Q-difference equation, and the actual implementation of this program is actually kind of complicated, and it's maybe with time being. Well, it suffices to say that there's essentially no computation in what would be called quantum key theory. So there's any number of geometric difficulties. But this is not what I'm going to talk about here. What I'm going to talk about is a conceptual difference. And the conceptual difference is that the actual Lie algebra we needed is not a Kac-Moody Lie algebra. It's not generated by real roots. And if you don't have a real root, you don't have a reflection. If you don't have a reflection for a root, your Weyl group will never be of the right size. And so, and the solution to this is kind of a little bit philosophical, and it comes from a very different part of well, for me, different part maybe. Looking from far afield, it's not that far. But it comes from another chapter, which I think is beautiful, worth discussing anyway. And so it's again the same story where you have a situation where two distinct branches of the tree of life, they meet. And here I'm going to talk about two distinct branches of geometric representation theory, because geometric representation theory, well, it could mean very different thing to very different people. It could mean, for example, a representation of ordinary Lie algebra by geometric operators, such as, for example, if you have a correspondence means a cycle in the product of two algebraic varieties, they may compose as generators in some Lie algebra, right? So that'd be a representation of a Lie algebra by correspondence. And it doesn't have to go from variety to itself, and it can go from variety to a different variety. As long as, so for example, it could be variety, could be labeled by a weight, and then whenever you go from one variety to go different variety, that weight that label is changing by the root. So that's perfectly well defined. I mean, after all. On the other hand, so that could mean one thing in geometry. So again, correspondence is nothing but a cycle in the product of two things. And it's composed just like matrices compose, and they act in cohomologies just like in the obvious way. And so, in fact, a matrix is like a cycle in the product of two finite sets. So if you understand matrix multiplication this way, you understand. The other thing you can call a geometric representation theory is representation of algebra that defined geometrically. For example, what could be a geometrically defined algebra? Say all differential operators on some variety. Right? And once you start doing this, there's no really need to restrict yourself to the world of actual differential operators, because there are many varieties. They're symplectic that locally look like they're cotangent bundled to something, and then you take functions there, you quantize them locally. It's like differential operators. But once you take global sections, you take global sections of that quantization, you get some non-commutative algebra, and for example, well, you get interesting algebras this way. You can get all universal developing of fine-dimensional Lie algebras, obviously, as just differential operators on flag manifolds. And so, and remarkably, these two things that seem to have very little in common, they come together in a marvelous piece of work by Okounkov and collaborators that has to do with quantization in large finite characteristics. So once you study, if you have an algebraic variety with algebraic simplicity form, you can study its quantization purely algebraically. You can also do it in finite characteristics. So that's and so we have some variety, which is secretly right now. So what my notation is now, I now have some variety n, which is algebraic symplectic. And remember, I was talking about ADE surfaces. ADE surfaces are symplectic surfaces, and the Hilbert scheme of symplectic surfaces is also symplectic manifold. So it makes sense to study their quantizations. And so anyway, I have some variety n, which I'm attempting to quantize. And when I do it in characteristic P, characteristic being large, or not when I do it, when Okounkov and Kaledin do it in large characteristic, what it turns out is you see a certain hyperplane arrangement. So there's a certain hyperplane arrangement scaled by P. Here P is 5, and so which is admittedly not such a large prime, but it is large for the purposes of this picture. So that you see such a certain hyperplane arrangement that has the property so that the actual quantizations correspond to points in my dots here, and the ones in the same alcove of this arrangement turn out to be Morita equivalent. In fact, so there's a functor from representations from one dot, from modules over one dot to the modules over the next dot, and that functor is an equivalence of categories as long as I don't cross a wall of this arrangement. And when I do cross a wall of this arrangement, I get a derived equivalence, but not an actual equivalence. So they're abelian equivalent within alcove, and they're derived equivalent across. Meaning that I get, every time I cross a wall, I get some operator that acts on everything, in particular on K theory. I mean, if you act, it's some. For every crossing a wall, I get. Well, in fact, I get an actual Fourier Mukai kernel, but right now I'm only going to take it as acting on K theory. And so I get a representation that K theories of all these guys can be identified, and can be identified by the K theory of my original manifold N. So I get a representation of a braid groupoid, if you want. Means to say, for every crossing every wall, I get a map, and this of course this has the property that if I go around a loop, I get an identity map. So I get representation of braid groupoid. And so, well, and the point about this arrangement, so the way I drew it, this is supposed to, at this point, it's a periodic arrangement. And at this point, we're supposed to compare and contrast it with like a fine hyperplanar arrangement for a fine Lie algebra. And the comparison point is that they're both periodic. The contrast point is that they're not symmetric. For a fine hyperplane arrangement, you can take any alcove to any other alcove. All alcoves are the same. Because if you cross every hyperplane, then in fact in that hyperplane I can in fact reflect. And that will be an automorphism of the whole story. But here is just some periodic arrangement. It might have some symmetry, but that symmetry group does not act transitively. So that's the bottom line. Instead of something which looks like a fine Weil group, you're going to get something which looks like a braid group of a periodic arrangement. It doesn't have reflections in it, not necessarily. But it does have commuting elements because you can, this thing is periodic, so you do keep the lattice in your groupoid. So it's not, you lose the reflection, but you keep the lattice, and we wanted the lattice. We didn't need the reflection. And so it's a ever ongoing work with Roma. That's I can't say it's in progress. It's in some kind of complicated function of time. Maybe it grows like log of t, and some such thing. But the idea is that these hyperplanes is something we've seen before. They're in fact the root hyperplanes of that Lie algebra G. And so G had some roots, some affine roots, and that be the space in which arrangements sit are exactly pic x, pic n. They sit in the same space. In fact, they're equal, and therefore they're also the poles of this equation. And the three things are the same. It's the monodromy of this equation. It's the monodromy of this equation. It's the action of this Bezrukovnikov groupoid, and it's some kind of version of the Weyl group, which is not exactly Weyl for this Lie algebra. And so, but while this work is ever ongoing, the actual part needed for the actual application is this part. It's just to define something like a Weyl group for the loop group for some kind of for. So you have a Lie algebra, has some roots. You have an affine version of that will have some more roots, and then you define something like a Weyl group in the quantized loop group of G. So that's our goal. And so we don't need to establish any side of this triangle. We just need to define an object here. And this can be remarkably defined with just completely universal formula, namely for every wall in this arrangement correspond a rank 1 subquantum group, or I don't know, rank 1 subalgebra in this. So this is quantized loop algebra of G. So this is rank 1 subalgebra in Z for every wall. And in fact, remarkably, there's some universal construction. So you can check. So if you give me any braided Hopf algebra, there's some absolutely universal construction. I can give you some element which would be a reflection if it was SL2, and be something else if it weren't, and it's the right thing to put. There's some formula which I'm just gonna skip. But the point is, there's just completely universal prescription just from starting from the tensors of this Hopf algebra. There's some way to write down some element, which is some generalized version of Casimir element, if you want, that has a series in Z, and the search. So for every wall there's a subalgebra. For every subalgebra there's some element, and the statement that this define our representation. So the statement is right. So the statement is this define representations of this braid groupoid on the K theory of my varieties. In the next theorem, which I'm still writing the proof, it's anybody saw the proof in cohomology can appreciate the amount of difficulty this thing requires. It is the case that the lattice part is the quantum connection. And maybe to give you an example, so let's do the Hilbert scheme of points in a plane. So again, this is the case where the Lie algebra is GL1, and its roots are all integers. So these are the roots, and they're all integers. Because, well, it has to be something of dimension 1, because Picard of the Hilbert scheme of points in the surface is one-dimensional. So for every integer, there's some root operator, and there, of course, there were not new guys. There were constructed operators constructed by Nakajima. So these are Nakajima operators that act on Hilbert scheme of points on C2, changing the number of points. Now we need to go to the affine version of it. an affine version. So if you had roots indexed by non-zero integers, then of course the affine root lattice will be Z2 minus the origin. Each one of these bits still defines a Heisenberg subalgebra, three-dimensional Heisenberg subalgebra of this kind. So each one of these says, I don't know, this is what, alpha, whatever, 4, 2 or some such thing. Well, I guess I got my numbering wrong. This is, no, 4, this will be like, what, 4, 3, right? 4, 2. Right, so anyway, it's kind of embarrassing. When they talk about enumerative geometry, you'd think you'd be able to count correctly, but anyway. So each one of them is a one-dimensional. Each one of these roots is imaginary root. Each one of these roots gives you a three-dimensional Heisenberg algebra, but has this commutation relation of this kind. The commutator of this root and the opposite root is just a constant. And the constant you write in this way. And the actual geometric realization of this operator, so this operator has been studied from various points of view, but if you look for a good geometric realization of them, you want to look in paper by the good. And so there's some particular operators. And so that for each wall, I mean, the walls are parameterized. You see, the roots, my roots are all integers. So their walls are where the inner product with the root is an integer, meaning the walls are parameterized by all rational numbers. And so, for each such wall, the corresponding wall subalgebra is just the algebra spanned by all these Heisenberg subalgebras as you go along a particular slope. And so the point is that the term in the analog for the Hilbert scheme of if anybody remembers that formula for, maybe I'll scroll back. It will take a while to scroll. So you see, for the Hilbert scheme of points, there will be a summation over n bigger than 0. There will be z to the n over 1 minus z to the n, and then Nakajima operators with minus n and n here, sitting here. And so it's a sum and things like Casimir-like things. And then if I go here, it's going to be a product. And again, I get the product of sort of Casimir-like things, and then terms which is like, well, this is z to the n over 1 minus z to the n. So it's a nice generalization of that formula as you could imagine. Anyway, to summarize, so what I tried to explain to you is that the life cycle of representation theory in its life cycle, and it has many forms. In one of the formats, it can be used to produce things which it was not intended to produce by nature. Nature wanted this guy to be a moth, but it became a threefold. So, and then of course this sort of selection, if you have a commercial use for an animal, that there's some sort of that it kind of impacts its evolution too. So the reason here is that this whole theory of this Notts-Katz-Moody type things were in largely just being developed for the needs to do enumerative geometry. People wouldn't necessarily care so much about this, I suppose, otherwise. And so this was what I was trying to say. And there's some things which I've didn't even have a chance to hint. And so maybe more what if I could, of course, maybe the most interesting part here is how do you actually wear silk clothes, or where do you wear silk clothes? I mean, if once you get that scarf, what do you do with it? So that's kind of an interesting story which will remain untold, and that's my hour now. So.